Discuss p-n junction in equilibrium with no applied voltage. P-type and n-type semiconductors are not of much use when used individually, as they are electrically neutral. But when fused together, they behave in a different way, producing a p-n junction. This p-n junction is used to manufacture versatile devices known as semiconductor diodes or p-n junction diodes or crystal diodes. Note that a p-n junction cannot be made simply by joining p-type and n-type semiconductors, as this introduces a grain boundary which severely reduces the utility of a semiconductor by scattering electrons and holes. Instead, the p-type and n-type semiconductors are joined using special fabrication techniques such as ion implantation or diffusion of dopants or epitaxy. A p-n junction is usually represented as: in p-n junction diode, cathode is the negative terminal at the pointed end of the arrow symbol, where current flows out of the device. Similarly, anode is the positive terminal through which current flows into the device. Thus, a p-n junction is a junction formed by joining p-type and n-type semiconductors together in such a way that the crystal structure remains continuous at the boundary. Note that the discovery of p-n junction is usually attributed to an American physicist, Russell Ohl, of Bell Laboratories. The related terms are: discuss classification of semiconductor in detail. To understand semiconductor and its classification, let us start with very basic thing, cloth. We know that these clothes are made from fibers, which are obtained from cotton. So cotton is that fundamental unit which is required to make cloth. Same is the semiconductor. Semiconductors are substances whose conductivity lie in between conductors and insulators. Semiconductors are basic elements of solid-state electronic device. We know that semiconductors are classified as intrinsic semiconductors and extrinsic semiconductors. Now we will study about intrinsic semiconductor. Intrinsic semiconductors are semiconductors in an extremely pure form. The commonly used intrinsic semiconductors are silicon and germanium. They are frequently used in manufacturing transistors and electronic products. An intrinsic semiconductor behaves like an insulator at absolute zero, that is, at 0 Kelvin, and as the temperature increases, its conductivity also increases. Let us discuss how. Consider the crystalline structure and energy band diagram of silicon, which has 4 electrons in the valence shell. Each of these 4 valence electrons forms a covalent bond with its 4 neighboring atoms. Thus, an intrinsic semiconductor behaves like an insulator at absolute zero. Now, if the temperature is increased to 300 Kelvin, we see that covalent bonds break as they absorb thermal energy. When an electron breaks the covalent bond and jumps from the valence band to the conduction band, a vacancy is created in the valence band. This vacancy in the valence band is termed as hole. These electrons and holes are also called free charge carriers because they are free to move throughout the crystal. Since an electron is a negatively charged particle, so the hole created by an electron is assumed to be positively charged. Such simultaneous generation of electrons and holes due to an increase in temperature is known as thermal generation. Thus, we can say that intrinsic semiconductor is an undoped semiconductor, where conductivity is due to the movement of thermally generated free electrons and holes. We have studied that an intrinsic semiconductor has negligible conductivity at room temperature, so it is not of much use. To improve its conductivity, impurity is added to a pure semiconductor, and this process is known as doping. Impurity can be of 2 types, donor impurity and acceptor impurity. Extrinsic semiconductor is basically a doped semiconductor on the basis of the type of impurity added. Extrinsic semiconductor is classified as N-type semiconductor and P-type semiconductor. Here we'll discuss about N-type semiconductor. But first, let us understand what donor impurity is. If the impurity consists of 5 valence electrons, then it is known as the pentavalent impurity or donor impurity. Some examples of donor impurity are arsenic, phosphorus, antimony, etc. Now, when a small amount of pentavalent or donor impurity is added to a pure or intrinsic semiconductor, the resulting semiconductor is called the N-type extrinsic semiconductor. Thus, an N-type extrinsic semiconductor is a doped semiconductor in which pentavalent or donor impurity is added to increase the conductivity of an intrinsic semiconductor. We have covered N-type semiconductor. Now we will discuss about P-type semiconductor. But first, let us understand what acceptor impurity is. If the impurity atoms consist of 3 valence electrons, then it is known as the trivalent impurity or acceptor impurity. Some examples of acceptor impurity are boron, aluminium, gallium, etc. Now, when a small amount of trivalent or acceptor immunity is added to a pure or intrinsic semiconductor, the resultant semiconductor is called a P-type extrinsic semiconductor. Thus, a P-type extrinsic semiconductor is a doped semiconductor in which trivalent or acceptor impurity is added to increase the conductivity of an intrinsic semiconductor. The related terms are Explain PN junction under forward and reverse bias condition. As we know that to operate a television, we require a remote. If we turn the remote, we can see a place for 2 batteries. So we conclude that for functioning of a device, we require an external source of power. In PN junction diode also, we require an external source of power. Thus, forward and reverse bias are the terms given to the arrangement of the external source of power in a PN junction diode. Firstly, the question arises, why do we require this biasing? When P-type and N-type semiconductor meet, PN junction is formed and depletion region gets created. The movement of electron and holes stop. Hence, flow of current also stops. To make the current flow, we require biasing. Biasing is of 2 types, forward and reversed. So let's start with forward bias condition. It is a condition when P region is connected to the positive terminal of the external DC source and N side is connected to the negative terminal of the DC source. And now let us have an idea about reversed bias condition. It is a condition when P region is connected to the negative terminal of the external DC source and N side is connected to the positive terminal of the DC source. Related term is explain the conductivity of semiconductor. We know that an electrical conductor is a substance in which electrons move easily from atom to atom. In general, conductivity is the capacity to transmit something such as electricity or heat. In conductors, the valence band and conduction band overlap with each other. But in semiconductors, the energy gap band is large as compared to conductors. Thus, conductivity of semiconductors is in between the conductivity of conductors and insulators, as the energy gap between valence band and conduction band is not very large. In a pure semiconductor, number of holes is equal to the number of electrons. The thermal agitation continues to produce new electron-hole pairs. The electron-hole pair disappears because of recombination. With each electron-hole pair created, 2 charge-carrying particles are formed. One is negative, free electron with mobility μn, and the hole with mobility μp. The total current density J within the intrinsic semiconductor is given as, where N is number of electrons per unit volume, P is number of holes per unit volume, E is applied electric field strength, and Q is charge of electron or hole. For pure semiconductor, where Ni is the intrinsic carrier concentration, is represented as. For N-type semiconductor, the conductivity is as. And for P-type semiconductor, the conductivity is represented as. Related term is. Define drift and diffusion currents. In a semiconductor, there are two types of current which is responsible for conductivity. They are drift current and diffusion current. Let's now discuss about drift current. Consider a semiconductor at room temperature, that is 300 Kelvin. When a voltage is applied across it, the free electrons present inside the semiconductor move towards the positive terminal of the applied voltage. This is because electric field causes the electrons to accelerate in free space. And as these electrons collide with the atoms continuously along the path, they get rebounded in a random direction and then drift in the direction of positive terminal. Current produced in this manner is termed as drift current. Thus, drift current is a type of current flow produced when electrons drift along, bouncing from one atom to the another. It usually occurs in conductors and semiconductors when voltage is applied. Let's now discuss about diffusion current. Assume that a concentration of one type of charge carriers appear at one end of a piece of semiconductor material as a result of charge carriers injection from an external source. Since the charge carriers are either electrons or holes, so they have the same polarity. As a result, there is a force of repulsion between them. This causes a tendency for electrons to move gradually or diffuse from the locality of high concentration towards the low concentration until they get eventually distributed throughout the material. This movement of charge carriers constitutes an electric current. Current produced in such manner is known as diffusion current. Thus, diffusion current is a type of current flow produced when the charge carriers diffuse from a point of high concentration to spread uniformly throughout the semiconductor material. Related terms are